Okay, so in 2.2, we are going to learn some of the shortcut rules. So yesterday, I did so many functions to help today's. So what we noticed is our derivative, if we had x squared minus 3x, the derivative was 2x minus 3. On this example, that derivative was 2x minus 2 from yesterday. On this one, I think this was example 3, our derivative was 4. On this one, on this one, this one, and our last one. Let's scroll this up. Okay, so what I said is like, hey, do you notice any patterns between the original function and the derivative? And you might not know, okay? But if we investigate, there are some. So like here, these are all parabolas. And what I notice is that the derivative always has a power of x. Now, sometimes there's a number in front, sometimes they're not. It looks like there's a lot of 2's, and then these didn't have numbers in front. So there is a relationship. We talked about yesterday that a derivative means slope. So on my line, I knew it was always going to be a derivative of 4, okay? But yeah, you might wonder why the concept of a derivative, which is the slope of a tangent line, is important enough to have an entire math course based on it. But later on, once we get to the applications, you will see the significance and how it could be used in business and other applications, okay? For this unit, we are literally going to be just learning how to take the derivative procedurally and computationally, but we're going to learn some shortcuts. Okay, so the first thing is the constant rule. So the constant rule says, well, if the derivative of a constant is 0, so if we have just a number, remember like y equals 9, that means I go up to 9, I've got a line, and hey, what's the slope of that line? It's always 0. Same thing, 0, if I was down at -8, and pi, remember, is a number. So this all is a number, and its derivative is going to be 0, okay? And slope of 0 is going to be important once we start looking at horizontal tangent lines and things like that. All right, next, functions for which the derivative exists. So when we have a denominator and we get a value, it's called differentiable. So a function can be differentiable for some values and not differentiable at others. So all we're caring about right now is the general slope. We might not be evaluating their derivatives. That would be a specific tangent slope, okay? And if it doesn't exist at a certain point, it's just called not differentiable at that point. So we are going to learn the first shortcut. It is called the power rule. So the power rule is when you have any base of x and it's to an exponent, a numerical exponent. So to take the derivative, what it says is you're going to bring that power down in front with multiplication, and then you're going to subtract 1 from the exponent. All right, so this is the power rule for derivatives. So let's look at here. It's x to a power, so I'm ready for my derivative. I'm going to bring the 2 down in front, and then I'm going to subtract 1 from the exponent. Okay, you don't have to show me that work. I'm just explaining it to you. That's it. Our second one, our notation for a derivative, we're going to bring the 6 down and subtract 1. C, it's just a power. So we can change our variable to t, and we can use s for our function. We still bring the power down and subtract 1. Now, on part D, we don't have a power, so you have to remember it is power over root. So it's x to the first power. And if the number is not written, there's like a square root. So the square root of x can be rewritten as x to the 1/2 power. And so now we can still do our power rule. We bring the 1/2 down in front, we subtract 1, and we typically don't leave our exponents as negative powers. So I get 1 over, the 2 stays, and remember, a negative exponent makes it a reciprocal. So we're going to bring that down. Typically, if the form starts in a root, our answer is a root, but be flexible. So y prime is equal to 1 over 2, and you might see it rewritten as the square root. Okay? That's why it says, in general, we do prefer to leave your answers with positive exponents. Whether you see the radical or not, you just have to be flexible. All right. So let's do the same thing with e. I need to rewrite that as a power. So that's like to the first. So if I bring that up, becomes x to the negative first power, and then we are ready for that power rule. Bring the negative 1 down, and when you subtract 1, you actually get x to the negative 2. So negative 1 stays, and that x squared is in the denominator. Same thing, we're going to bring this up, and we're ready for the power rule. Bring the negative 3 down, subtract 1, and rewrite that with positive exponents. All right, we're going to combine. We know it's a negative because it's in the denominator. That's t to the first power over the third root. So our derivative is negative 1/3, subtract 1, and we don't write mixed numbers. We always write improper. So I get negative 1 over 3, and then we'll just make that 4/3. They probably wouldn't change that back to root, but just be flexible. And our last example starts out, and our derivative is negative 3/4 x subtract 1. And so we get negative 3 over 4x to the 7 over 4. Okay, now we're going to do the constant multiple. So what that means is we might have a number in front that's being multiplied by a power. Okay, and so that says, hey, just keep it being multiplied and then do your power rule normal. So on example number 1, I'm going to make this bigger. Okay, we've got to rewrite the original. So the 2 stays, and I'm going to bring this up with a negative exponent. So our derivative says to bring this down and to multiply them together. We're still going to subtract 1 because it is a power rule. So rewrite that without negative exponents, and that's our derivative. Now this one you can think of as that 4/3 and then x cubed being separate. You don't have to rewrite that though. So our derivative, we're going to bring this down with multiplication. So 4/3 times 3 is just 4. And we're going to subtract 1. So that's done. This, because we don't have a parenthesis there, that really is like negative 1 times t to the 5th. So we can start off with our power rule. Bring that down and multiply, and subtract 1. The exponent is not negative, so we are done. This can be rewritten as 5/3, and then we need to bring that x up. Okay? So our derivative, we're going to bring down and multiply, and subtract 1. We do rewrite the negative exponent. Now, on F, because this is a group, I actually need to simplify that first. We can't do quantities yet. So 3 cubed is 27, and x cubed. So I can rewrite that as negative 5 over 27, x to the negative 3. Oops, I forgot to move over. I'll do that in a second. So we're going to bring that down. So we're going to multiply. So I get 5 times 3 is going to be 15 over 27. We'll reduce in a second. Subtract 1, x to the negative 4. So divide by 3, we get 5 over 9. And then that x is going to come down. We'll make that x to the 4th. All right, and then 40, remember that's t to the 1st, so 1 over 2, and since it was in the denominator, that's a negative. So our derivative, we're going to bring it down and multiply, and subtract 1. So we'll rewrite this with positive. The negative 20 stays, and the t to the 3/2 goes in the denominator. All right, I left 2 out. So let's go and do those. So we rewrite this as 4x to the 1/2. So our derivative, we're going to bring that down and multiply and subtract 1. So our derivative is 2 over, and I can write x to the 1/2, or I can write 2 over root x. Either one's good. On h, our original problem, we're going to rewrite as 12x. Remember, it's power over root, and it's negative because it was in the denominator. So negative 5 times 12 is negative 60 divided by 3 is negative 20, and subtract 1. So I get negative 20 over x to the 8/3. Okay, the next section, I'm going to do some of this, and then I know my 15 minutes is going to be up. So this is a sum and difference rule, and it's kind of just like limits. So what this basically says is whether I'm adding or subtracting, I can do each of them separately, okay? This is not true of multiplication. So on part A, we've got a power rule, so you bring the 2 and we subtract 1. This one, we're going to multiply, subtract 1, and then this is like x to the 0. So if I bring that down and multiply, and remember a constant was always 0, this x to the 0 is 1, and so our derivative is going to be 2x plus 5. Eventually, you'll be able to do that all in one step. All right, let's look at B. They're all being added or subtracted, so we can do them each with the power rule separately. We're going to bring the 4 down and subtract 1. Multiply by bringing the 3 down and subtract 1. Bring that down with multiplication, subtract 1. That starts as a 1, so bring the 1 down. And remember, when I subtract 1, I get x to the 0, which isn't there. This term also starts as 0, so when I bring that down, I'm going to get a plus 0. So if you can get used to that, you can save a step. All right, let's look at part C. Now, part C is different. So